In this work, we present PhysHead, simulation-ready Gaussian head avatars reconstructed from multi-view images. We propose a novel method for generating compositional head avatars with strand-based hair geometry, fully animatable and driven by graphics engines. Digital characters are an important part of the virtual world. Especially, the head and face region carries a lot of information for storytelling, communication, and emotions. Believable and realistic facial expressions, head motions, and moving hair are key. In movies and games, skilled artists model these different aspects with layers that provide animatability of the face region, as well as physics-driven hair dynamics. However, automatic avatar reconstruction methods struggle to provide such an output and only model the facial expressions while assuming static hair. There are two main reasons for this. First, these methods do not disentangle the head from the hair. Second, their chosen hair representation is not suitable for physics-based simulation. More specifically, prior works such as Gaussian avatars and Gaussian head avatars reconstruct animatable head avatars using a single layer. Although they produce impressive results, the hair is modeled as part of the face. In contrast, our method PhysHead represents the head with a layered model. A bald human head controlled by a face parametric model, and strand-based hair controlled by a physics engine. Concurrent methods like Haircup and Mega that try to disentangle the face and hair region achieve impressive avatar results, but they do not model hair with a representation that can be animated by physics to extrapolate to novel poses and external forces like wind. Our method addresses this gap by using a strand-based representation for head avatars. We propose the first method to reconstruct animatable head avatars with a strand-based representation from multi-view images. The reconstructed avatar has two components, the head and the hair. The head is controlled by a classical 3D MM. The hair consists of strands that can be directly simulated in graphics engines. For appearance, both the head and the hair use 3D Gaussian primitives for photorealism. We track facial expressions using a Flame multi-view face tracker. Since Flame does not include hair, it is suitable for modeling the facial region. For a single time step, we reconstruct the hair using neural haircut. Our pipeline has two main components. First, representing the head with rigged Gaussians and optimizing them to obtain an animatable bald avatar. Second, reconstructing strand appearance with color consistency regularization. Naively optimizing the head layer without hair results in an incomplete representation as the observations are only partial. However, when the hair moves during animation, these missing regions become visible. Therefore, obtaining a complete head layer requires recovering regions that are not captured. To address this, we propose using a vision language model. Specifically, we use NanoBanana's editing capabilities to remove hair from the training images. However, the outputs of the model are not always multi-view consistent and are costly to query for every expression. Therefore, we optimize an appearance proxy for the missing regions. We query the visual language model for one frame and optimize a single texture of flame using a differentiable rasterizer. This texture, together with the tracked flame mesh, is used to remove the hair in all other training frames by merging synthetic flame views with the original images using Poisson editing. After obtaining the bald head images, we rig Gaussians to the flame model and optimize for head appearance. This produces a complete animatable head avatar. Concurrent work, Haircup, also reconstructs missing head regions, but uses SDS-based losses. Due to the characteristics of its generative reconstruction pipeline, it can exhibit artifacts and often produces limited variation in skin tone across subjects. In contrast, our approach preserves each subject's true skin tone and achieves more accurate head completion. Additionally, our hair is represented as strands, making it directly compatible with physics engines. In the second step, after reconstructing the animatable face avatar, we optimize hair appearance using color consistency regularization. For simulation, we sample sparse guiding strands and simulate them in a physics engine, which allows us to generalize to unseen motions. We compare our hairstyle reconstruction with Gaussian haircut. While Gaussian haircut respects hair masks, it struggles to model individual strands consistently. Its appearance decoder cannot fully capture the hair's visual detail. Although the outer shell resembles the intended hairstyle, the inner strands often receive random colors, including skin tones. In contrast, our method diffuses color from visible strands to the occluded ones, producing a more realistic and coherent hair appearance. We compare our results with Gaussian avatars and Gaussian head avatar. Although both produce photorealistic results, their hair is static, whereas PhysHead can synthesize dynamic hair. Since our method uses explicit strands, it supports appearance and geometry editing by manipulating structured strands. It also supports applications such as wind simulation. Thank you for watching.